All right, looks like we're all done. Let's see how we did. We are not bad today. 50-50. What a perfectly balanced score. Not too many people got the second one. Looks like most people got the first one. So the bamboozle with the first one was obviously that the index that I was trying to get was 1, and just like arrays, array lists also start at index 0. So I said clone item and then new string r.getI. I passed 1 in there as my argument for the clone. The item at index 1 would be butter, not bread. So if you guessed bread because it's the first thing, well, no, it's actually the 0th thing. We still use that same convention as we would use for arrays. For the remove part, if I had put a return after that remove statement, it would have been fine. But remember that if you are looping through an array list and you try to take something out and then continue to loop through it, then you get that concurrent modification exception. And so since I didn't return, I would end up with that concurrent modification exception. So the answer was that I would get an exception in that case. And the reason for that we looked at a little bit last time is because anytime you pull something out of an array list, it has to scoot all the items over in order to make room for the next items to come up. So it's always got no empty spots. Everything always scoots over to accommodate the empty spots as you remove things. That means that you need to do something special to accommodate for the fact that as you've removed something, everything else is shifted over to take its place. And the best way to do that is to iterate through your array lists using an iterator, which we talked about a little bit last time, but I wanted to go over it just a tad more, give you a better picture before we move on. So you can call the .iterator method on any list in Java. ArrayList is just one kind of list, but you'll see others at some point down the road, probably in the next CS class. And an iterator just lets you visit the items in the list and has a couple of other utilities as well that'll maybe come in handy to you at some point too. But the most important one is the ability to visit all of the items in the list, and more importantly, to remove items from the list safely. So you can type an iterator just like you can type an array list using those fancy little bracket things. So you could also omit those, and then it would not be able to infer correctly that we are looking for a record, but you could fix that by adding a cast. So those are two approaches. I almost always prefer to type the list if possible, but it's actually possible to have an array list of different things. You could have an array list, for example, let's look at your last homework where you had 3 different kinds of marbles. You could have an array list of all 3 different kinds of marbles. You might still want to do some kind of casting. Maybe you even want to cast the clickable or movable. That's one possibility. So occasionally you might use the casting approach instead, but if you can, I recommend that you type your iterator. So our records array is made up of records. Let's make sure that our iterator is looking through records as well. It's more convenient. And then instead of a for loop, we do a while loop. You've probably seen this before in something like scanner. While the iterator has more items, so while the list has more items, that would return true. Iterator.hasNext. We pick the next item up, so record next equals iter.next. That grabs the next item that's available in the list, and then we can do whatever we want with it. So I did our comparison there, and I did, rather than ArrayList.remove, so note that this is not records.removed, I did iter.remove, and it doesn't take any arguments. And what makes it safe is that it just removes the last item that was grabbed by next, and then performs all the accommodations necessary to continue. So it will visit the next item correctly and all of that good stuff. So it's a little bit different syntactically, and it's a little complicated with the little, brackets and the fact that you have this fancy thing called an iterator, but it's really not that complicated. You're just looping through just as you might with the for loops. It's just a slightly different syntax, and it's safe to remove things as you go through. Now, one of the disadvantages to the iterator is that you don't have the index here at all, right? So you could kind of get the index by just saying like int index equals 0 and then sort of counting as you go, right? But then you run into that same problem when you remove something, everything shifts over to the left, so you'd have to subtract 1 from the index to continue to be accurate. Generally, when you want the index, you want to use one of those for loop approaches instead. But with lists, generally speaking, we don't need the index. We're just using it as a list of items, and the index is less important to us. So, something to consider. There's a different kind of approach to looping through ArrayList depending on what you want to do, and that's one of the things that makes them so darn complicated to work with compared to basic arrays where the approach is almost always the same. Any questions on ArrayLists before we move on to our next thing? Okay, cool. We'll try to use them again a couple more times before the end of the semester, and then the homework, the last homework, which I'll post tonight, will involve ArrayLists. So make sure you understand at least something about them. There'll probably be an ArrayList question on the final, too. Okay, so this is going to be our particle simulator. And today we're going to move a little bit quickly. We're going to move a little faster than we usually do so that we can finish a kind of complex example, and we're going to do the same thing on Thursday. On Thursday, I'm going to make some kind of game, so board game, arcade game, low-budget video game. So think about what game you want to make on Thursday, and then I'll probably take a poll at the beginning of class. So if you've got any games you want to see made, you want to see something boring like tic-tac-toe, I can do tic-tac-toe. You want to see something more interesting, we'll do something more interesting. So just post any of your suggestions in the chat between now and class on Thursday, and we'll do whatever it is that's the most popular one. Particle simulator. We haven't done a lot of animation in our painting and swing class yet. So today we're going to do a little bit of that. The very simple trick to animating is that you just repaint at the end of paint components, and we do something like this. This actually eliminates the need for having to call repaint manually anywhere, which is pretty cool. But probably looks weird to you if you think about it, because this is an infinite loop, isn't it? You've got paint component calling itself. Well, through the magic of threading, which you won't learn about until the next CS class, this actually isn't a problem. Our paint component method is able to continue to call repaint without getting stuck in an infinite loop, and we're not going to go into the details too much there. Just know that it's something we're allowed to do. It's something that lets us animate. Okay, I'm going to start by creating my little particle object. Where's my particle? I'm going to make this an ellipse. Call that display. And we're going to have some variables that we need to track. I'm going to go for the option of tracking the x and the y myself, I guess, since it's something that we haven't seen quite as much. And then, since this is a physics simulation, I'm also going to have my velocity. I'll call that vx and vy. Or I guess I can call them something a little more complicated. Velocity x and velocity y. Difference between velocity and speed is that velocity has a magnitude, so we could go positive or negative on x, positive or negative on y. And those two things together give us the direction that the particle is moving. So do our constructor here. We'll take an x, take a y, and we'll start all the particles off at a random speed. So I'll give a range for that. Call that starting speed max, and let's say 5. I don't know what a good value is, but 5 seems reasonable. So our x's get set up. Whoops. That's annoying. Maybe I should name them something different. I'll think about it as we continue. And I want to be able to have a negative velocity too, so I'm going to say math.random times starting speed max. It gives me between 0 and 5, but I actually want between 0 or negative 5 and 5. I actually want between negative 5 and 5. So what I could do is I could probably change my range and subtract, or I can do something like this. I can go times 2 minus 5. Okay, let's do the math there. So if I roll a 0, then I get negative 5, right? 0 times 5 times 2 is still 0, minus 5, that's negative 5. Okay, so that's the lowest I could get, negative 5. If I roll a 1, it'll be 1 times 5 times 2, which is 10, minus 5 is 5. Okay, so I got between negative 5 and 5. A stupid hack, but it works. And I'll do the same thing for the y. And really, I shouldn't use that magic number 5 there. I should avoid using those whenever I can. But the times 2 in this case is not really a magic number. It's actually part of the math equation. Turning it into a variable would probably be unnecessary. The fact that it's doubling is what I'm trying to communicate there. And I'm going to set my display up here. I'm going to give it a default size. X, Y, and then I'll copy the starting size in for both dimensions, so it has the same width as it has height. Okay, and then every frame, the particle is going to change position in proportion to its velocity. So its x position changes by its velocity, its y position changes by its velocity. So we're going to say something like move, or I don't know, advance, or something. I'll just call it move. And it doesn't need to take any arguments because I already have the particle's velocity. So every frame, x plus equals the velocity on the x-axis, and y plus equals the velocity on the y-axis. And I can document that as well. Updates the position of the particle relative to its velocity. And then if I really wanted to be fancy, I could link the velocities there. I think you can link two in one comment like that. Let's see if that was correct. Nope. They need separate ones, darn. But that wasn't so bad. Okay. And I should probably document my constructor too. Creates a new particle at the given x and y position with random starting speed and the size of, and then I could link to the size as well. Always helpful to link to these things because down the road I'm going to forget what the starting size is, and it's going to be nice to look it up without having to switch to this class. So in addition to movement, you also have acceleration, right? You have the ability to accelerate. What happens when you accelerate? In either chat, what happens when you accelerate? In the meantime, I'll write some of the other boilerplate stuff, but what happens when you accelerate? Get a little practice with our interfaces in. Yeah, the velocity increases, or changes, actually. It could go down or up. So we're going to have to take some arguments in there, aren't we? So let's go back to accelerate and take the change in the velocity. So I'll call it delta x and delta y. and our velocity, or I guess I could be more simple and call it something like AX and AY for acceleration. Up to you how you want to do your naming. I tend to lean on the longer side whenever I can. And it's possible that AX and AY are going to be negative, depending on whether you accelerate or decelerate. You could slow down too. And of course, once you get slower than 0, you start moving in the other direction, since velocity can take you left, right, or up, down. And you could, if you wanted to accelerate only on one axis, just pass to 0 for the other argument, which is going to come in handy. We'll see when we do gravity. To get a little practice with interfaces, I'm going to use that drawable functionality that I had before, because that's all our display is going to really need. And let's make a starting color for all of these. And I'll set everything to a random color at the beginning as well. Always hard to count to 6 when I do that. 6 Fs for the random color. Okay. Nice. And we'll just set the fill to that color. Whoops. Got a little bit ahead of myself. And then fill in the display. And then we'll set the color to black. And fill that in as well. Or draw the outline, I guess, not fill it. Okay, now I did make one little mistake here, is that I'm updating the X and the Y positions, but I didn't actually update the display's X and Y position, which is why I tend to avoid this approach, because you gotta do everything twice. And one of the ways to make that a little bit less tedious is to have an update display method, and that always just sets the display's X and Y to the X and the Y that you're tracking. So display.x equals X, display.y equals Y. And the only reason I even have that X and Y is just to avoid having to type display.x and display.y everywhere else. So I call that anytime we move to make sure that the graphics update. Don't have to call it anytime the velocity updates, because that doesn't actually change the thing's position. Okay, that's going to be a reasonable start. Let's create a bunch of these. And I'm not going to do that in my display. I'm going to make this a little bit better of an object-oriented example. We've done a lot of creating our arrays of things and such in the display class, but really that's not a great idea, because that's mixing our logic with our UI, with our user interface. And we want to avoid mixing our logic with our user interface whenever possible. So let's make a class called, let's say, Simulation Manager. This is going to actually track the simulation and update the position of particles and everything. And the only thing that the display class really is going to be responsible for is drawing things and then communicating to the Simulation Manager whenever there is an input. There's my array list. I'll import it. And then we'll take an argument of how many particles that you want. So this will create a simulation with that many particles. Starts a simulation with the given number of particles. Now, since I'm also setting all of the particles' positions here, I either need to take a panel as an argument so that I can take its width and height, or I need to just pass in the width and height. I'm going to opt for the approach where I take the panel as an argument. So I'll take a JPanel display. I guess I'll call it display panel, just so it's clear that it's a panel, and so I can search for it by looking for the word panel. And I can either take it as an argument or link it manually. I'm going to take it as an argument here because it will help me for setting up the simulation. I'll name it the same thing. So this dot display panel equals display panel, and then we're going to loop through for as many particles as we have, as we're trying to add, that is. And we're going to create new particles for all those positions. So I have my little particles array there. I'm going to add. I don't have a particle yet, so I'll make a new one. That's going to be a new particle, and then remember I have to give it an X and a Y position. So I'm going to access my display panel, and I'm going to check its width for my maximum X position. And then I'll check the display panel's height for my maximum Y position. And I want a range somewhere in between there. So to put it all together, probably put this on separate lines. I'm going to do math.random times those in order to get a random position somewhere on the panel. And it kind of groups it all into one line with the auto formatter, which makes me cry a little bit, but that's okay, I guess. Okay. And this has a chance to spawn the particles off the screen a little bit, which is not great. So let me fix that a tad. I actually don't want to go all the way up to the width of the panel. I want to go all the way up to the width of the panel minus the size of the particle, because then I don't get clipped off the end of the screen. So it's going to be the width of the panel minus the starting size of a particle, which I conveniently made static so that I could access it anywhere without having to have a reference. So there, and then now I have to pan over because the auto formatter did not do a good job here. Let's see if it puts it on a new line now. Alright, cool. That's a little bit better, but still not great. Okay, and that gives me a large collection of particles to work with. Alright, let's go back to my display and add a reference to the simulation manager as well, because they're probably going to have to communicate in both directions. I'll call this the simulation for short. And now let's link everything and set it all up together in the driver. So I've already made the panel. You got to make the panel first, since the simulation manager takes the panel in the constructor. So simulation manager sim equals new simulation manager. And then I was supposed to take a few arguments there. What do I need? I need how many particles? I'm going to go with, let's say, 200. And then which panel? That's the one that I just made. I called it panel. Did I spell this wrong? Yes, I did. There's probably an extra A in there somewhere. Let's call it simulation to be consistent, since that's what I called it elsewhere. It's nice to name your local variables consistently too. So even if it's not the same variable, even if it's not a global, it's nice to know that anytime you've got something locally, you're going to name it approximately the same thing, as long as there's no reason to name it something else. That way you can very easily guess, if you're deep inside of a relatively long method, what the name is going to be. And then I also need to link panel to the simulation manager. So this is like that homework that we had some time ago, where you had to link the two panels together. Well, can't link them both in the constructor, so there you go. Alright then, let's go to my display. And I can draw all the particles a couple different ways. Let's do a way that we might not have done before, using the interfaces. This goes back to a solution you could have used, and probably should have used on the last homework. I gave you that example where I had the array of marbles, but then I also had the array of drawables and clickables and movables. So we have our list of drawable items, right? And then we want to populate it with all of our different drawable particles. So let's say we want to stick all of our drawable particles in there. For that, we'll make a method for it. Register particles. We'll call it registered drawable particles, or even, let's say, register drawable items. Perhaps there are going to be other things that get drawn later besides particles. Not today, we don't have time for that, but may as well plan ahead. So the description of this is going to be adds everything that should be drawn to the screen to the Drawables array list. And then I should probably link it here. Anytime you are using a global variable or modifying a global variable inside of a function, it's not a bad idea to link to the global variables that you're modifying, especially when it's kind of straightforward like this, that the method's called register drawables, the thing it's modifying is called drawables. It's nice to have a reference to it. Okay, so we actually have to loop through the array of particles that we have. And then we want to visit all the particles in our simulation. So for particle P in the simulation particles list, and then this all assumes that the simulation is not equal to null. We could provide that extra check there. We could do something like this, where if simulation is equal to null, we just return and nothing happens. It's good to add those kinds of sanity checks, even though in this example we don't expect that to happen, and it shouldn't under normal circumstances. On the other hand, having something like this can make it harder to debug, since it'll just fail without any kind of error. You just won't have anything getting drawn. And like many of you noticed with the homework, since all particles implement the drawable interface, you don't have to do anything fancy in order to convert them to drawables. You simply add the particles to the drawables array, and now they're treated as drawables instead. Since the particles all implement drawables, straightforward thing to do. And you could have done the same thing for the last homework too, so the clickables, the movables, etc. You could set them equal to the particle there. All right, so now we've got all of our particles registered. Drawing them is pretty straightforward. So for every drawable D in our drawables array list, we're going to call the draw method, e.draw G. And then we're going to repaint. Now I also want to advance the simulation every time that this ticks. So this has actually become something like a frame. Start of the frame, and then end of the frame. So we think about animation and video games and simulations in terms of something we call frame. A frame is basically one tick of the simulation, one iteration of it simulating or doing what it's going to do. And we've simulated that here in Paint Component because it's going to keep calling itself over and over again. It might be convenient to have a frame counter. So we'll start at 0, and then we'll move up every time by 1. If I was to print this out, like so, and run it, you'll see the frames advance really, really fast because we don't have anything going on, and I got a pretty strong computer here, so Swing's able to go real gosh darn quick. If we wanted to limit it and perhaps make it go at a slower speed, we could. But first, let's see what happens when I don't limit it. Let me just go ahead and advance the simulation each time. So for that, I'm going to have a new method in my simulation called tick. Tick is going to do everything that the simulation does on one frame. So this advances the simulation by one frame. And the main thing that happens right now is that all of the particles inside the particle array move up by one spot, or wherever they're going. So every particle moves according to its velocity. So if we do that here, if we call our simulation.tick and let it advance, we're going to see that these particles move really gosh darn fast. Hold on, let me get these guys to show up first. Let's see, we've got nothing on the screen yet. Where did they all get drawn to? Let's see if all the particles are getting registered successfully first. They're not. So see, that's a dangerous thing, isn't it? That it just failed gracefully there and didn't register anything. So let's see why that might be. Well, that's simple. It's because I never actually called this method anywhere, did I? Womp womp. Alright, so I'll do it here in panel after or here in the driver after I set up the simulation. So I've got I just definitely bungled that. Register the drawables there. Okay, there they are, all referenced. And if you blinked, you probably missed it. Let me get rid of that print statement, and I'll show you again. The particles all... Uh-oh. Oh, keyboard thing. Yes, don't buy a Razer keyboard. Okay, they all started there, and then they whooshed out, and they were gone. Goodbye, whoosh. Whoosh. There they went. So first of all, they're not starting in random places. That's a problem. So let's go back to that. They're not starting in between the width and the height. They're starting, you know, in the corner up here. If I had to reckon why that was, considering this looks right to me, I would say it's probably because I forgot to set the display to the right place. Let's see if that's the case. No, it seems to be in the right spot. It's at X and Y. So let's print it out and see what we're getting for the starting positions. Getting X and Y. There we go. So we're getting a pretty wide range there, but not the range I'm expecting. I'm not getting the width and the height as ranges there, so that's probably not the issue. Let's go back to here and see perhaps I'm not getting the right width and height, so I'll just try the width first. See if maybe I'm not getting the width and height I'm expecting, and indeed I'm not. I'm getting zeros all the way. And the reason for that is because the panel doesn't have any width and height. Actually, not only after the constructor finishes, the panel doesn't actually have any width and height until it gets packed down here. So I could just move this all until after the frame is finished, which is what I'm going to go with here. That way the panel actually gets built successfully, and there go all my particles. There they went again. Look at them go. Whee! Alright. Or I could have passed the width and height in as arguments instead of passing in the panel, but this works, and I'm happy with it. So let's continue. Okay, and then I should probably leave a warning for future programmers. Make sure that the panel is instantiated and the width and height are accessible. Accessible? That's the one. I'll put a little break there so that that's on a separate line. There you go. Maybe a double break that's floating down there. Okay, the next order of business is going to be to first of all get the particles to bounce when they hit the sides, and then possibly to mess around with the frame rate so that it's not moving quite so fast. So I'll get them to bounce off the sides first so we can see just how fast it's actually going, and then maybe we'll do something with the frame rate too. So for them to bounce off the sides, that's going to be a part of the particle, the individual particles behavior. is that when it hits the side of the chamber, it bounces. The problem is that it doesn't know when it hits the side of the chamber, because the side of the chamber is given to it in the panel, right? And of course, we don't have any reference to the panel here in the particle. So what do we do? Well, we could give it a reference to the panel as well. I'll put my statics all together. We could say jpanel panel, etc., and put it here. Or I could also just give it the information that it needs, which is the max width, max height. And I want to set those up at some point. Why don't I just set those up in the constructor? So I'll set up the... I probably shouldn't call these max width, mat height. I should probably call these max x and max y. Yes. That seems more friendly, because this is the largest x and y position that they can have before they're considered to be off the screen. Okay, so max x. And this dot max y equals max y. Hope I spelled those right. Looks like it. And now to update my simulation manager here, I got to specify those. And of course, the maximum x is the width of the panel, and the maximum y is the height of the panel. Ooh, that's a lot. Might turn off the auto formatter and make that look a little bit prettier. Let's see, what is it? At auto formatter. Can never remember what it is. Yeah, it's all right. At formatter off. I'll live with it. So for the particles maximum x and y position, I got that, but perhaps I want to update those down the road, so if the panel gets resized or something. So let's do that as well. Let's say update max values, and we'll take an updated x and y, and I'll set those down here. And I'm actually going to call this method from my constructor so that I don't have to have two methods that do the same thing, or two pieces of code that do the same thing. So anytime I update my x values, I'm going to do it through this method. So this updates the boundaries that the particle has to stay inside. Note that the left and top boundary is always 0. So this is the bottom and right boundaries that the particle has to stay inside. And this also helps because now I have extra documentation on my constructor. I don't just have like a series of tasks that you have to look through individually. I can see that you're updating the positions. I see you're doing this stuff, a little bit of this stuff. That's all instantiation. And then if I wanted to know what else was happening, I could hover over this particular methods documentation, or I can just read it. It's relatively clear that I'm updating the max values there. All right, so all that was an aid of making sure that I can move successfully, that I move within the boundaries of the panel. So what happens when you hit the side? What happens when you hit the side? So if x is less than the 0, the left side, or x is greater than the max x, what happens? Likewise for the y's. How do you bounce? Kind of a physics question, kind of not. How do you bounce off the side of the chamber? Notice how much typing I ended up saving by going with an X and a Y here, because I'd have to do display.x there, and display.x there, and display.x there. So it's nice to just have them all update at the end, so that I can use X and Y here throughout. How do you bounce when you hit the sides? Yeah, you just flip the velocity. So on the x-axis, if you hit the side, velocity x equals negative velocity x. So not to be confused with minus equals. Again, they give it some spacing and all that good stuff. So velocity y equals negative velocity y. Now we can get a pretty cool looking simulation already. Look at them all go, but they're going so fast. So very, very fast, aren't they? One way to make it go slower is just to crank up the number of particles. Look, if I have 2,000, it's going to go a bit slower just because the computer can't handle it as well. But, you know, Swing is surprisingly performant, so even something like 20,000 probably won't crash. Might take a second to come up, though. Let's see. No, that might have been too many. Alright, well, let's try 10,000. Maybe that's more doable. You know, it's actually probably the printing to the console here that takes up the most resources. You'd be surprised how much console printing takes up. See, there you go. Just take out that print and it's going. It's definitely crawling, though, because now it's gotten to the point where it can't even finish a frame, probably like 10 frames a second or something, based on looking at it. But boy, does it look amusing. Alright, and right now, if I resize the panel, nothing happens. Interesting, right? So at some point, I'm going to have to... I'll write a to-do here someplace. Maybe I'll put it at the top. To-do when the panel is resized, inform all particles. Okay, so first let's deal with the making of the simulation a standard speed, so giving it an actual frame rate. And this is accomplished most easily by just giving the frame a number of seconds, basically, that it can elapse to. So I'm going to take a long frame start. That's going to be the system time when the frame begins. And the very first frame begins when the application starts. Okay. And then I'm going to, at the end of every frame, take a long and then the current time. That's going to be the time at the end of the frame there. And if the current time, you can see why I use while instead of if here in a second. If the current time minus the starting time, which I think I called frame start, is smaller than the duration of the frame that we want to have, and let's say that we want to have 60 FPS, so I'll call this FPS and set it to 60. Static final int FPS is 60. Well, the long current and the long frame start are in milliseconds, so if I want 60 frames a second, then how long is each frame? Well, it's going to be 1,000, that's milliseconds, divided by the frame rate. That gives me the number of milliseconds in one frame. So while that it is true that not enough time has elapsed, so while current minus the frame start is smaller than the amount of time you want for a whole frame, then we're going to just redo current. So we just stall, basically, and do nothing until current is large enough. And then once this is finished, you are free of this loop, and you can begin to draw the next frame. I'm going to get the start of the next frame right there. Alright, so that makes it include the entire duration of drawing the next frame from the beginning. So repaint is the very next thing to call after that. And this is going to be basically stalls until we want to frame to achieve a constant frame rate. So this is not always the way we do it. Sometimes we do want to draw as fast as we can, but for a simulation like this, we want everything to tick at a certain speed. So I've got my particles bouncing around here, and they look pretty nice. I have a null pointer exception somewhere. Let's check it out, because everything still seems to work. But what's going on? Well, on the very first few ticks, there is no simulation yet, because the driver doesn't link those guys together until later. And when the panel is first generated, the simulation doesn't exist. So I think more broadly what we should do is probably just check if it's null here, and then return. Let's see if that works. So if simulation is null, we're going to return. And that avoids the error. So looking good there. Okay, bounce, bounce. Look at them go. Nice. Couple things to note here. First of all, they clip off the side of the screen over here. They actually go a little bit past it. Right? A little bit, not too much. If we wanted to fix that, well, when you hit the side of the screen there, we don't want you to hit all the way to the max x, all the way to the max y. Let's set those a little bit differently. The maximum is actually not all the way, because that's off the side of the screen. Just like we did when we were setting up the particles. The maximum is actually minus the size of the particle. And if I do that here, I get to avoid thinking about that elsewhere. And now they hit the side there and don't clip through, so that's cool. And I don't have to think about it in, say, the simulation manager when I'm setting it up, or in the constructor over here. I know that's just part of the updating max values logic. And I might leave myself a comment there because it's a little bit confusing. Subtract the particles size so they don't clip off screen. Cool. Alright, let's make some cool graphical improvements. Let's change the background to white. That looks nice. Let's turn on anti-aliasing. Rendering hints. How do I do that again? Let me look it up. Swing anti-aliasing. It's like set rendering hint something. Gotta turn on ray tracing too, right? Even though it didn't exist for decades. Set rendering hints, and then you gotta do this, I think, yeah? I just found that on the internet. On. Okay, we got our RTX on now. Look at that. They look even more beautiful than ever before. But they're bouncing around with random speed. That's not super duper fun, so let's do some more for them. Let's also make them accelerate with the force of gravity. So every tick, I want to also have gravity affect these guys. So I'll call this void, well, I can actually do it inside the tick just to save some space. So let's say before the particles move, they get affected by gravity. So we're going to add gravity, and then we're going to update positions. Let's set gravity to something. So we're going to go with our float gravity. Doubles, everything else has been a double. Double gravity, let's try 1 and see how intense 1 is. So for all the particles in the system, they're going to accelerate. We already have an accelerate method. gravity doesn't affect you on the x-axis, but it does affect you on the y-axis. So every tick, you accelerate due to gravity. Let's see what that looks like. Whoa. They just get faster and faster because they don't lose any of their momentum every time they hit the ground. They return back with all of their momentum intact. And then we're starting to note one of the first bugs, that sometimes things kind of get stuck at the top there and then they just kind of jitter around. A certain extent of that is unpreventable because Swing is not really a game engine. It's not designed for really nice collisions. But how do we make it so that the particles actually don't bounce back with their full force, so that they actually lose some of their momentum every time they hit the sides of the chamber? What can we do for that? And I'm only making everything public for convenience sake. A lot of this probably should be private, but just to get something cool implemented, I'm just leaving everything as default. So, what can we do? Well, one thing we can do is add a basically dampening factor or friction or whatever you want to call it. I'll leave the terminology to you physics people. And this is going to determine how much of the particle's momentum it keeps every time it bounces. And so instead of just multiplying the velocity by -1 every time to invert it, I'm also going to multiply it by the dampening factor every time the particle bounces off the side of the chamber. And that means that it's going to lose a small percentage of its velocity every time it hits the ground. And so they're going to get slower and slower and slower until they're just kind of stuck down there. If I make it larger than 1, so if I made it 1.1, then it'd be like moon gravity, and you would actually get higher every time you hit the ground, and you'd accelerate super duper fast, because gravity's really strong here. So, whoa, look at it go. And if you made it really, really low, like 0.2, well, then every time they bounce, they'd lose pretty much all their momentum, and then just get stuck down there forever. Now, in regards to that bug where they occasionally get stuck in the sides and then start jittering around, well, that happens for a reason that's kind of tough to figure out. It happens because sometimes particles can clear 0, they can just shoot past 0 without getting past it again when they come back out the other side. So let's say that a particle gets past 0 and it gets past 0 all the way to like -35, for example. So it goes really far past 0, right? And that's because it's moving very quickly. Once it makes it out there to -35, we're going to keep flipping its velocity every frame, every time it moves. And then it's just going to kind of jitter back and forth while it's stuck on the edge there. So what we really want to do is flip your velocity when you're less than 0, and you're moving in that direction. How do we know if you're moving in that direction? How do we know if you're moving towards 0? Any ideas? How can we determine that you are moving towards 0? We only want to flip your velocity if you have hit the left side of the chamber and you were moving left when you struck it. Otherwise, there's a chance that you clip all the way through the left side, and we register you as having struck the left side of the chamber even though you're well past it, and then you just keep flipping your velocity back and forth, and that's not good. So how can we do that? How can we determine that you have been moving left when you hit it? Again, kind of a physicsy question, but not particularly a physicsy question. If your velocity is negative, then you're moving left. So if it's less than 0, then you must be moving left. And then likewise on the other side. Wow, you guys practically typed exactly the same thing in Discord. That is really impressive. And if you're on the other side, then your velocity has to be positive. And we'll do the same thing on the y-axis. And that's going to cut back a lot on the random particles jittering on the sides. But again, you can never really get rid of it because things kind of have a tendency to get stuck and swing. That's just how it goes. So we'll see a little bit less of the random jitteriness now. They actually do tend to bounce. Once they get kind of stuck in the bottom, once they lose all of their momentum, then we also tend to see them clip through the bottom as well. Okay, so we've got them bouncing, we've got gravity. Let's add the ability to interact with the simulation a little bit. Let's say when you click, we're going to create a zone that draws the particles in, I don't know, some direction, or draws them towards that zone. Can we do that? Probably not. No, that's too complicated. That's got like vector math and stuff. Let's just say when you hit a key, so if k dot get key code equals key event dot vk, let's go with a. Then we're going to turn the wind on, or let's say that raises the power of the wind, and then the other direction will reduce the power of the wind. So we'll go with increases wind, decreases wind. Alright, what do I want wind to do? Let's start with a wind of 0. The wind pushes all the particles in that direction. Add gravity and wind. So we're just going to accelerate them with wind on the x-axis and gravity the other way. And then for our wind increasing and decreasing, we'll go with, just call it update wind or change wind. Let's go with change wind. Change wind, double delta. Delta is a nice way to make it clear that you are changing it rather than updating it, because delta is always the difference, right? So that makes that a little bit clearer that you're updating something rather than changing it. So if I just took something like wind here, then it's kind of ambiguous. Is it plus equals or equals internal? And you could read the comments to figure that out. I'll read the comment here. So adds the given value to the wind's strength. Wind plus equals delta. So every time you hit one of those keyboard keys, it's going to, in this case, we'll go with simulation.changeWind. We'll add, let's make it small. Let's go with 0.2. And then the other way, we'll go with negative 0.2. Alright, so if I run this now, and then I hit the A key a few times, I can get them to smash against that side. And if I hit the S key a few times, eventually the wind will blow them over there instead. And A key, S key, A key, S key. I can probably print out the way that the wind is blowing to make it a little bit more clear. The wind is blowing, and then add the wind there so that we know what direction it's going in. It'd be nice to add it to the panel, but it's fine, I think, to have it in the console. Let's turn down the bounce on the particles too. Let's get it back to something like 0.95 so they stay up in the air longer. And you can see the wind blowing in the different directions. Hey, look at them go. Alright. And I could add something else too. Let's say I can turn gravity on and off. Let's go with gravity on and off with the D key. Turns gravity on or off. So for this, let's say we're going to toggle gravity. And we could do this a few different ways. We can either set our gravity to 0 and then set it back to 1 when we have to do it. So that would be one approach. Or we can have a Boolean that determines whether it's on or off. I'll go with the Boolean approach. Let's say gravity on equals true. If our gravity is on, then we're going to do the usual thing with our acceleration. We'll add the wind and the gravity. And if not, then we'll just do the wind, and gravity will be 0. That makes this method pretty straightforward. Gravity on equals not gravity on. So if it's true, it becomes false. If it's false, it becomes true. And then we can call it here to flip it. Toggle gravity. So gravity's off now. Particles bounce to the moon. Add some wind. Turn gravity back on. Turn back off. Turn back on. Turn back on. Okay. One more thing, I guess, before we finish for the day. Hopefully you enjoyed our little physics playground here. Again, keep in mind, next time we'll do a game, so decide which game you want to do. And also next class I'm going to give you an opportunity to fill out those evaluations. So if you've already done that, or you want to do it in your free time, because maybe you want to type a little more, just save your confirmation email that you get, because there will be a little extra credit involved for filling those out. So just hold on to that confirmation email, or whatever you get for confirmation after you fill out those evaluations. Okay, last thing I'm going to do is to support particle collision. And this is one thing that I never asked you to do this semester, to collide two circles together, because there is no built-in contains method for those two circles. So let's go with public Boolean. I'm not going to call it contains, I'll call it collide. And we'll say ellipse 2D. Well, we'll call it particle other, and then I'll take its ellipse out of there. So ellipse 2D ellipse other, ellipse 2D dot double equals other dot display. And again, I didn't ask you to check collision at any point between two ellipses, but it's actually not that hard. So if you have, let's say, show you in Paint first. If you have, let's say, two circles and you want to tell if they have collided with one another. So if I want to tell if these two circles have collided with one another, boop. Well, all I'm really doing is checking if the distance between their two centers is something. Let's think about what that might be. So all of these circles have a radius coming up from their center, right? And if you've collided, that means something in terms of your distance from the center to the other circle. So if this circle is touching the other guy there, what does that mean? As soon as they touch, what is this distance here as soon as the two of them touch? It's the distance between the center points of the two circles. It's their two radiuses combined, right? As soon as the two circles touch, the distance between those two center points is their radii combined. And the radii is half their size, and so on and so forth. So we've got a little bit of a formula here to see if two circles have touched. So if the distance between the two circles is the sum of their radii, then we must have touched. How do we get distance again? That's kind of the annoying part. Definitely one of the reasons why I don't like to make you do this. So what is the distance? Double distance between this and the other. Well, we have a formula for it, right? A little hypotenuse formula thingy. 2D distance formula. Let's Google it. You don't even have to click a link, it just comes up right there. There we go, right? Square root x1 minus x2, y2 minus y. That seem familiar? Should be pretty common. Pythagorean theorem, all that good stuff. Alright, so math dot square root of, and then we wanted to do the two particles centers, so that's going to be the ellipse others center x minus this displays center x, and all of that is supposed to be squared. I guess I'll start putting this on separate lines for convenience. All of that was supposed to be squared, so I can do math.pow, or I can just multiply it by itself, right? That has the same effect as squaring, multiplying something by itself. So I'm going to go with the easier option, and multiply it by itself. Easier, but definitely not shorter. In fact, let me store these as variables so I can make it slightly shorter. Let's go with double other center. You know what? Even shorter. Let's go with x1 double x2 equals display center x. And I'll do the same for the y's. Now that's going to be a lot shorter, so it's x2 minus x1 squared again, so I'm just squaring it by multiplying it by itself, and then it's added to the square of the y's. And that's how you get the distance. And if the distance is bigger than the sum of the two radii, then the circles must be touching. So if the distance is not bigger, sorry, smaller than other well, they're all the same size in this case, so the sum of the two radii is starting size over 2 plus starting size over 2, which is just starting size. Then we're going to return true. Quite convoluted. Well, that's all the time we have for today. I'll add something cool that they do when they smack into each other before I upload it. But I'll upload this example too if you want to pull anything from it. So again, next time, decide what game you want to do, and at the end of class there you'll probably have 10-15 minutes to fill out the evaluations. So start compiling your thoughts, and if you want to fill them out early, please do so. Just hang on to your confirmation. Next homework goes up tonight, and I will see you next week.